There we go. A recording of the meeting will be posted on this website here, the hub for A-StoRM. And there's a lot of other good information on the hub as well. Next slide. Welcome to the members of the public who have joined us this afternoon. You'll remain in listen-only mode throughout. We encourage you to use the A-StoRM email address to send us your questions and comments. You will have the opportunity to formally comment on draft regulations during the regular public review process. Next slide. And a welcome and thank you to our stakeholder consultation group members. A reminder to please stay muted when you're not speaking. We'll be pausing for your questions a few times during the presentation today. You can type your questions into the chat at any time or wait until those pauses and raise your hand. Raise hand, I believe, can be found under reactions at the bottom of your screen. And it would be nice if you could turn on your camera when you ask a question. And maybe the first time you're called on to ask a question, you could remind us of your name and your affiliation. Next slide. You bring diverse experience and skills to this group, so we value your full participation. Please, we want to hear from you during this whole process. Next slide. Today, after some opening remarks from MDE, we'll have a pretty long presentation, punctuated with pauses for questions. You can see what will be covered here. I'll warn you that today's presentation is pretty technical, but it is the foundation for future policy discussions. We do have another meeting coming up scheduled for November 15th. We'd really like to get through this whole presentation today. If we don't get to all of the stakeholder groups' questions today, we can start next month's meeting with those questions. And if you think of new questions between now and then, we can also take those at the beginning of the November meeting. And you can also contact Ray Barr at any time. I'll remind you of his contact information at the end. Now I'm pleased to introduce Mr. Lee Curry, Director of the Water and Science Administration at MDE. Lee.
Sure, thanks, Kathy. And thanks to everyone that joined today. One, I just cannot stress enough how important your role is in terms of modernizing Maryland stormwater regulations. And I view it as, this group and your work and your insight are really critical in ensuring safe and resilient communities, both today and into the future in Maryland. And again, that really gets at, in one part, modernizing the state stormwater regulations in response to climate change. Now, we are thinking about a variety of things, three in particular, when we're talking about our stormwater regulations. One is design storms, using the right rainfall. You're going to hear a lot about that today. Two, are the designs working as intended? And then three, knowing where urban flooding is likely going to occur and thinking about it more holistically so that we can come up with smarter solutions. We continue to monitor and look through the literature, and it was brought to my attention that just last week, I think it was, Northwestern University added to this growing body of science related to stormwater and conveyance capacity and climate change. And one thing they note is, as we know that as the planet continues to warm, the atmosphere can hold more rainfall, and that rainfall is becoming more intense. So that raises some critical questions in terms of whether our existing infrastructure can actually handle the downpours for the future. Actually, can they handle the downpours for today and also the downpours for the future? And one thing I was pleased to hear was one of the authors said communities may need to turn to simulated precipitation events to really guide our decisions related to our building decisions. So it's thinking about, what is the rainfall that best represents today, but also what is the rainfall that best represents the lifespan in terms of the infrastructure that is being designed and built. We know that the review, the revision, also the discussion of these stormwater regulations are needed. And this is why, again, you play such an important and critical role into this because of the perspectives that you bring to the table. The last time this group met, we discussed in a broad overview what was new with respect to the stormwater management law, what it required, what the department was working on to actually to implement the actions in that law, and then thinking about responsible and smart regulatory changes that we are going to be and will be presenting you for consultation. One thing that we heard loud and clear from you was that you wanted more detail on the scientific foundation that drives or is driving the changes to Maryland stormwater management regulations and the program in general. So today's meeting is largely going to be focused on that. It's digging into the details, as Kathy pointed out, digging into the science and behind the stormwater regulatory changes. So today we're going to have, who I'm very pleased to present, Stu Comstock, who has been doing just a tremendous amount of thinking with his team about this. He brings to the table more than 30 years of experience in stormwater management, in hydrology and hydraulics. And it's just, I feel very fortunate that he's at the department and is part of the team and leading this effort and really leading some of the work on with the Regulation Technical Advisory Group. So he's going to get into the details today on precipitation data, the information that we've gathered, some of the questions that have come up. And it's not just precipitation, it gets at design storms. And again, thinking more broadly, that foundational element in terms of our stormwater design, which is the design storm. So I look forward today to a robust discussion. We're looking forward to your feedback, for your input, for your questions. We want it to be a dialogue. Again, there's a lot of detail in the presentation, so please feel free to ask questions, and we look forward again to your feedback. So at this point, I think the best thing I should do is turn it over to Stu to carry on with the rest of the conversation. And again, Stu, thanks for digging into the details today.
Thank you, Lee. It's been fun. So good afternoon. In the last meeting, I understand you discussed the nuts and bolts of the Senate bill law, the new stormwater law. Today, I am going to focus on what the department is doing to identify the most recent precipitation data and update Maryland's stormwater quantity management regulations. In today's meeting, we are going to discuss the most recent precipitation data and why it should be used in the state's stormwater management program. We're going to talk about the effects of that data on determining the maximum flows or peak discharges that are used for storm drain and stormwater management design. We're going to talk about climate change projections and their effect on peak discharges, and how this information is being used to develop better stormwater quantity management regulations. As I mentioned, we will be discussing the latest precipitation information, climate change projections, and how they affect stormwater management. The precipitation data is important, but it is just part of a larger picture. And to see that bigger picture, we need to get into the weeds a little bit. We need to discuss some basic hydrology concepts concerning precipitation frequency, storm intensity, and storm duration, and how they are used for storm drainage and stormwater management design. First, some useful terms. During today's discussion, I will use the following to describe how rainfall and runoff are used to determine flow or discharge. Storm frequency, or how often a storm will occur, a 10-year storm. Storm duration, or how long a storm lasts, typically expressed in hours, a 10-year, 24-hour storm. Storm intensity, or how much rain is falling at any given point during that storm. Distribution curves, These are the graphs showing the change in storm intensity over time during a storm. And finally, hydrographs. These are the graphs showing the change of flow over time for a given storm event. There is a saying, if you don't like the weather, wait 5 minutes. Actual rainfall patterns are difficult to predict and even tougher to use for designing things. To get around this problem, engineers have synthesized several parameters to predict how water will flow in a given situation. Precipitation data will include design storms of specific intensities, durations, and frequencies that are based on statistical analyses of rainfall patterns. Distribution curves that standardize how rain falls during a storm event. Rainfall increases to a peak and then decreases. And standardized hydrographs that are used to predict how runoff flows from a watershed, including the unit hydrograph most commonly used in design. These are important issues. I have highlighted these and other important points throughout this discussion using a megaphone. What parameters are needed to determine flow? When drainage system capacity is exceeded, the excess or overflow can back up and cause local flooding. Runoff is determined by land use and land cover. The amount of runoff from a given area is determined using runoff curve numbers that are based on specific land use and land cover relationships. During this presentation, I will be using a sample 10-acre site for demonstrating how precipitation and downstream flow are related. The pre-developed condition for that site is wooded with a runoff curve number of 70. The developed condition for that site is residential, and I have used a runoff curve number of 82. These values will determine how much runoff comes from the site. Flow is a function of how long it rains, how intense it was raining, and how runoff concentrates and flows past a location. Please note that in natural settings, the relationship between these various parameters is not linear. So, before we identify the most recent precipitation information and why it matters, we need to understand the difference between actual rainfall and the rainfall data used for design. There are certain challenges: quantification, lack of pattern, landform influence, and the limitations of monitoring systems and data. Actual rainfall events are difficult to use for engineering design for many reasons, including those I've talked about. To get around these issues, design storms were developed for analyzing flooding or designing storm drainage and stormwater management systems. These design storms are synthesized and include parameters based on the amount of rainfall, how long the storm lasts or its duration, the occurrence frequency of specific events, and how that rainfall is distributed throughout a storm or its intensity. This table shows the primary differences between the design storms used for our purposes and actual storm events. Natural storms can be of any duration, from a few minutes to a few days. However, for design purposes, we need to use a standard duration. And for reasons we will discuss, the 24-hour storm is the default commonly used in flood assessment and engineering design. Distribution, or how rain falls throughout a storm, is also important for determining the magnitude and timing of the flow of runoff. Intensity and duration refers to the frequency or chance that a storm will happen in a given year. For example, storm drain and stormwater management design may be based on a 10-year, 24-hour storm. And finally, scale is an important factor for the aerial coverage of a storm event. Precipitation frequency data is based on reports from gauge stations in a region and may not reflect smaller flashy thunderstorms that occur locally. Storm frequency. This is an important design parameter. It is based on a statistical analysis of past records and gauge-based data, and the average interval of a storm event of a given rainfall can be expected. To determine rainfall frequency, rainfall gauge-based data sets are analyzed to determine hypothetical rainfall events of specific frequencies. These statistical analyses are distilled into an intensity, duration, frequency, or IDF curve. This information is often also expressed in a table. Storm frequency is the chance of recurrence in a specific interval. For example, we often talk about a storm being a 100-year event. That means the storm has a 1% chance of occurring in a given year. It has a 10% chance of occurring one or more times in 10 years. And it has a 63% chance of occurring one or more times in the next 100 years. Storm frequency is used for decisions during the design of stormwater management, stormwater conveyance, and flood management projects. For example, when using the 10-year storm for design, the assumption is that there is a 10% chance in any given year that the design conditions will be exceeded. For flood assessment and engineering design, the most commonly used duration is the 24-hour storm. This shows an example of an intensity duration frequency or IDF curve for the 24-hour storm. The x-axis shows the recurrence interval, and the y-axis shows the rainfall depth associated with the different recurrence intervals. The black line is the precipitation estimate. The red and green lines represent the upper and lower boundaries of the 90% confidence interval. For example, the 25-year 24-hour storm would have a rainfall depth of 6.5 inches. A storm with a 1% chance of occurring in a given year, or the 100-year storm, would have a depth of 8.5 inches. So let's talk about rainfall distribution. Natural rainfall has no set pattern and is not necessarily reproducible. For this reason, it is difficult to use actual rainfall for designing infrastructure or for analyzing flooding. Rainfall distribution curves were developed to estimate how rain falls in a given event. Historically, 4 different distribution curves were developed to characterize rainfall patterns across the United States. These curves are used to determine how runoff occurs during a design storm. The distribution curve assumes rain falls in a set pattern, slowly increasing with the highest intensity at the middle of the storm and then tapering off until the storm ends. These curves help synthesize the relationship between rainfall and runoff at any location. This relationship is used to determine the magnitude of the flow or runoff or discharge at any point during a design storm. Because distribution curves have the highest intensity at the center of the storm, peak flows typically occur near that point as well. For example, for a 24-hour design storm, we can expect the peak flow to occur near the 12th hour. This is the Soil Conservation Service's standard rainfall distribution curve for a Type 2 storm. This is commonly used in the Natural Resource Conservation Services, or NRCS, TR20 and TR55 hydrologic models. I will talk more about this specific curve, the Type 2, in a few minutes. However, let's talk about it in general terms. Because of its shape, it is also known as an S-curve. It is used for modeling how it rains during a design storm. In this example, I've used a 24-hour storm. The x-axis shows the duration of the storm in hours, in this case, 24. The y-axis shows the cumulative or total rain over time fraction of the storm that has fallen, with the entire storm having passed by the 24th hour. At the beginning, rainfall is light and slowly increases in intensity till around the 10th or 11th hour. Then the period of most intense rainfall occurs in the middle of the storm, between the 11th and 13th hours, with the highest intensity at the event's midpoint, in this case, the 12th hour. Please note that the largest fraction of rainfall is in the center of the storm, where the rainfall is most intense. And in fact, for the Type 2 curve, 45.4% of the 24-hour rainfall occurs in this 1 hour. This is also where the peak discharge typically occurs. From the 13th hour on, the storm slowly decreases until the entire storm is passed and we've had all of the runoff. Rainfall frequency data and distribution curves are used to develop the relationship between the rate of flow of runoff and cubic feet per second over time. Hydrographs are the graphs that show the rate of that runoff that is flowing past a specific location. Engineers and designers develop hydrographs to determine what the potential maximum or peak discharge may be and when it will occur. The process for developing a hydrograph is very complex, and we will skip over that for now. You'll thank me later. What is important is to recognize how hydrographs are used for analysis and design. This is a partial list of the types of hydrographs, but includes the most commonly used ones for watershed work. Natural, these are obtained directly from flow records at a gauge station. Synthetic, they are simulated based on watershed parameters and specific storm characteristics. And unit, developed on theory and does not necessarily reflect specific conditions. However, it is the most reproducible. Can you guess which one engineers use to design storm drain and stormwater management systems? Yep, we use a unit hydrograph. In fact, most hydrologic models like TR20 and TR55 use a specific dimensionless unit or index hydrograph to develop individual hydrographs for specific uses. This slide shows the Soil Conservation Service's dimensionless unit hydrograph. Originally developed in 1957, this is used in the NRCS methods TR20 and TR55 and other models. It is the default in the standard for drainage system and stormwater management design. The graph represents the flow of runoff over time. This is like filling up a bucket of water with a garden hose. The orange line represents how much water is needed to fill the bucket. In this case, the bucket is full at the 5th hour. The blue line represents how fast the water from the hose is filling the bucket. As the bucket fills, the hose is slowly turned off. The y-axis values are expressed in the ratio of discharge at a time t over the peak discharge. Also on the y-axis in this case is a mass curve showing the accumulated volume of runoff at time t versus the total volume. The x-axis values are expressed as time over the time to peak discharge, or the time from the beginning to rise to the peak discharge, and this is set at 1. The area under the blue line is the volume of runoff. This is a runoff hydrograph representing woods versus residential lots. We can compare how the discharge hydrographs change as land use and runoff conditions change in a watershed. In this example, a 10-acre wooded site with a runoff curve number of 70 has been developed into residential lots with a runoff curve number of 82. We have chosen the 2-year 24-hour storm, which has a rainfall depth of 3.2 inches. Because of the land use change, the runoff depth has increased from 0.83 inches to 1.54 inches. The volume of runoff has also increased from 0.69 acre-feet to 1.28 acre-feet. For the given storm, the wooded site produced a peak discharge of 5 cubic feet per second at 12.4 hours, while the developed site produced a peak discharge of almost 17 cubic feet per second at 12.2 hours. Please note that although the peak discharge has increased by almost 12 cubic feet per second, both peak discharges occur around 12 hours. This is a function of storm duration, in this case 24 hours, as the rainfall distribution curve has the peak storm intensity at 12 hours. These characteristics are important as we discuss the transition to newer precipitation information. So, in summary, natural weather patterns are unpredictable. Don't like the weather? Wait 5 minutes. Engineers use synthetic parameters to predict the flow of water. Precipitation data. These are the design storms of a specific intensity, duration, and frequency that are based on statistically derived information, typically in IDF curves. The 24-hour storm is the most commonly used for engineering design. Rainfall distribution curves reflect the pattern of rainfall throughout a given storm event. Rain increases to a central peak intensity and then decreases. Rainfall distribution affects the maximum flow or peak discharge associated with the rainfall event. And finally, hydrographs. Unit hydrographs do not necessarily reflect natural conditions. And the SCS dimensionless unit hydrograph is the most commonly one used for design. Now, I know that was a quick overview of some of the basic hydrology concepts concerning precipitation frequency, storm intensity and duration, and how they are used for storm drainage and stormwater management design. However, it should place all of us on the same page as we discuss updating precipitation data, climate change projections, and the implications for Maryland's stormwater management program. Are there any questions before we move forward?
Thanks, Stu. This is our first pause. I don't see any questions in the chat yet, but I see that Neil has his hand raised. Or had his hand raised.
Yeah, it's hard to tell when you click. It's saying that just highlights it for a second. Sorry about that. So, Stu, I have a question for you. First, that's a great presentation. I'd say it's easily as good as the Marissa one that I've seen a couple of times. My question is this the right approach to this whole thing? I mean, we're using the existing tool TR55, TR20, and we're adapting it for this rainfall. Is this the right tool to use for us?
That's a good question. And please note that TR55 and TR20 and a lot of the proprietary models that are based on the similar foundation are equipped to handle the new rainfall data. I have used basically TR55 and TR20 to develop a lot of the hydrographs I'm showing here. Now, there are other models here that are continuous simulation and much more intense or detailed. There's a fine line between using a very detailed model for flood analysis and the modeling we do for smaller stormwater management practices. And so
I think
in presenting this today, I'm trying to keep it the lowest common denominator there.
Right, but I think the challenge to it is it's really important is that upland flooding, not flooding it within the floodplain, but we're seeing so many more instances of upland flooding where it's not backwater, but it's water coming off sites.
Yeah.
And they're very small watersheds, they're micro watersheds that are flooding people's houses that are overwhelming the storm drain systems. And there's storms that are just thunderstorms, whatever fancy title you want to come up with for them, that are these that occur over an hour or 2 hours, which I don't think is reflected in that model.
Hold that thought, all right? Because that's a very good question, but if I answer it now, it'll be a spoiler alert. And I don't want to spoil the fun for everyone.
Spoil it, but I'm just saying, these are great tool, but at the same time, I think the climate adaptation or climate change is occurring upland, and it's occurring more from very small areas. And,
it's something we are discussing, and well, like I said, this is a spoiler alert. We'll talk a little bit about that as I move forward in the presentation. So hold that question, and if you have a similar question at the end, we can discuss it further. Any other questions?
I see that Jen has her hand raised.
Thanks, Kathy. This is Jen Denninger with University of Maryland Sea Grant Extension. And thanks to still a pretty technical drive-by of the processes that you're using, but I think I understand a little bit more. I am curious though, when you're talking about the use of the synthetic or the unit hydrographs, those, in my very limited understanding, are not based, or they're not showing you real conditions. They're a model. And so I'm wondering how well the models are aligning with the real conditions so that we can trust the models as we move forward?
That's a very good question, and also one that's under discussion at various levels. Again, when we're updating regulations or policy, we have to consider oftentimes the lowest common denominator and how things are designed. These dimensionless unit hydrographs have been calibrated. They have been used for years, but you have to understand that, again, the design of storm drain systems and stormwater management does not necessarily tie back into what you're actually seeing in the field in a natural event, because there's just too much going on. But again, these are all issues that are up for discussion, and I will talk a little bit about all of that as we move forward.
Okay, I guess it would be my hope that we could simulate or reproduce more real conditions with our modeling, as you said, since it's under discussion. But thank you.
Anything else?
Neil, is that a new question or is your hand still raised from before?
Still raised, but she
Oh,
made a
okay.
great point. with
Yes,
like
it is a good point.
that there are models available that can do what she's talking about.
We'll talk about it.
Okay,
Okay.
Steve. Well, it looks like everybody wants more.
All right. Okay. One of the first tasks that the department is addressing through the A-StoRM effort is identifying the most recent precipitation data available. However, before we talk about the latest and greatest information out there, we should also look at what is currently being used. Quick summary. NOAA Atlas 14 is the most recent precipitation data. Spoiler alerts here, smaller, more frequent storms changed minimally. Larger, less frequent storms, they increased. There are new rainfall distribution curves. We'll talk about them, kind of go over some of these points. And I think the biggest point here is that everything we're talking about with the precipitation data provides the foundation for the climate change models. So with this understanding and this summary, let's move forward. Currently, the state stormwater management regulations do not identify the source of precipitation data that should be used in engineering design. The rainfall depths that are shown in Table 2.2 in the Maryland Stormwater Design Manual were taken from the U.S. Department of Commerce Weather Bureau's 1961 publication technical paper, or TP40, Rainfall Frequency Atlas of the United States. It was published in May of 1961, and it is as old as I am. The majority of the rainfall data used to develop TP40 was gathered from 1938 to 1957. There was some older information incorporated into that, but the majority of it came from that period of time. It is important to recognize that even now, most rain gauges record daily, for example, 24-hour rainfall. Hey, it rained 3 inches yesterday. However, historically speaking, most users only needed 24-hour rainfall values for large-scale modeling of the flow of water for flood assessment and floodplain determination. And most drainage system design, like storm drains, culverts, and stormwater management features, is still based on a 24-hour event. This is a scanned image of a page from my personal copy of TP40. This particular page shows the variation in the 10-year 24-hour design storm across the state of Maryland. Nice little green patch right down here. Please note that the state of Maryland, there are 3 lines or isopluvials that are used to define the 10-year 24-hour storm event. We got a 4-inch, we got a 5-inch, and we got a 6-inch. Everything in between is interpolated. This will be important when we compare precipitation data. Please remember that rainfall data is only part of the equation. This shows the approximate boundaries of the 4 Soil Conservation Service rainfall distribution curves across the United States. They are 1, 1A, 2, and 3, with 1 and 1A being the least intense and 2 being the most intense. All of Maryland uses the type 2 distribution curve. The type 2 distribution curve is based on the information found in technical paper 40. However, and this is important, there is not much documentation on the development of the type 2 curve. Even the Weather Service says the best thing we got is a paper from 1973. I want to put this in perspective, folks. This is a family photo of my mother programming an advanced computer system in 1956. Okay. Same year, the SCS type 2 distribution curve and a lot of the foundation of what we use today for modeling was developed. This computer was used to model the flight path for the X-13 Vertijet. This is the first jet to take off and land vertically. At that time, most hydrology was still done with pencil, paper, and a slide ruler. And I want to point out, most children's toys have more computational capability than this unit. The most current precipitation data available is NOAA Atlas 14, Volume 2, Precipitation Frequency Atlas of the United States, Ohio River Basin, and the surrounding states, published by the U.S. Department of Commerce, National Oceanic and Atmospheric Administration in 2004 and updated in 2006. NOAA Atlas 14 uses a much larger period of record. As you can see, the longer period record ranges from the 1890s to 2000. It includes more rain stations and gauges, 93 in Maryland alone, and is based on a more robust statistical analysis of the data. Atlas 14 includes point-specific information and robust mean values for each of Maryland's counties. I want to make a point, however. Much of the data used to develop Atlas 14 was still reported in a daily format. Hey, it rained 3 inches yesterday. This is a map of the stations in Maryland used to develop Atlas 14. This is a lot different than the 3 lines on the old TP40. I have posted a link. This is a screen capture of the online version of Atlas 14, known as the Precipitation Frequency Data Server, and I posted a link to this page. The Precipitation Frequency Data Server, or PFDS, allows immediate access to the precipitation frequency data for a point of interest. Here, I have selected, you can see my little red cross here, right here, a point in Baltimore County. Actually, it is the Towson station that provided daily data from 1907 to 1995. This is clearly light years ahead of TP40. This is a comparison of the 24-hour design storm precipitation estimates from TP40 and NOAA Atlas 14. The values in red are the larger of the 2 rates. For the more frequent storms, like the 1, 2, or 10-year storms in the majority of counties, the precipitation estimates provided by TP40 are actually larger than that reported by Atlas 14. In most cases, this difference is only a few tenths of an inch. For the counties that are east of the Appalachian Mountains, the precipitation estimates from Atlas 14 are greater for the larger, less frequent storms. This is attributed to the larger state data set that was used to develop NOAA Atlas 14, showing the effect of tropical storms along the eastern seaboard of the United States. However, NOAA Atlas 14 didn't just provide updated precipitation data. The information and analyses used to develop the older SCS rainfall distributions, like the type 2 curve, are not consistent with the newer information derived from Atlas 14. To correct this, NOAA also developed new rainfall distributions based on the improved quality and quantity of information used to develop Atlas 14. Because this information is different, the different rainfall distribution curve sets, type 2 curve is incompatible with NOAA Atlas 14. NOAA's rainfall distribution curves must be used with the NOAA Atlas 14 rainfall rates. These rainfall distributions range from the most intense, NOAA A, to the least intense, NOAA D. Most of Maryland is represented by NOAA C. Western Maryland, is represented by NOAA B, and there's a small bit of the eastern shore that is represented by NOAA D. Again, the NOAA Atlas 14 rainfall values and rates should be used with these distribution curves. Remember our earlier discussion about rainfall distribution curves. This graph shows the NOAA B, C, and D distribution or S curves. Again, on this graph, the x-axis shows time in hours for the design storm, in this case 24 hours. The y-axis shows the cumulative rainfall fraction that's fallen over the 24-hour period. As before, rainfall intensity slowly increases to a maximum at 12 hours and then decreases until the 24th hour. As you can see from the steepness of the curves, NOAA B, which is the red line, is steeper through the central part of the curve, and NOAA D, which is the blue line, is the least steep of the three curves. While they appear similar, these three curves will produce different results as shown in the next few slides. This table compares the effect of using different NOAA distribution curves on an identical site. As you can see here, as you move from west to east, the new distribution curves result in a lower peak discharge from identical sites for the same rainfall event. For example, in Western Maryland, there was a peak flow of almost 13 CFS. Throughout most of Central Maryland, that same rainfall event, because of the difference in the distribution curve, resulted in a peak discharge of about 11.5 CFS, or cubic feet per second. And finally, on those two portions of Wycomico and Worcester County, where you used NOAA curve D, the peak discharge was 10.3 CFS. Because a different distribution curve is used, where a site is located affects the different peak discharge produced by a given storm event. I want to show this in a different image. This shows the effect of each NOAA distribution curve, again, on the same identical 10-acre site. The site conditions, runoff curve number, runoff volume, are the same for each site. The runoff depth is 1.38 inches. Runoff volume is 1.15 acre feet. The only thing different is the rainfall distribution curve used to determine the rainfall runoff relationship. Again, NOAA B has the greatest intensity rainfall, and the hydrograph shows a peak discharge of 12.9 cubic feet per second. NOAA C, which again covers most of Maryland, results in a slightly lower peak, 11.6 CFS. And finally, because NOAA D has the lowest rainfall intensity, the peak discharge is also the lowest at 10.3 cubic feet per second. Now, let's take a look at how NOAA distribution curves compared to the SCS Type 2 curve that is currently used to design stormwater management infrastructure. On the previous slides, we were showing the difference between the NOAA rainfall distribution curves. This shows the difference between the older SCS Type 2 curve, which is the red line, and the NOAA C distribution curve, the blue line that represents Central Maryland. The SCS Type 2 curve has a much higher intensity of rainfall through the center curve than the NOAA C curve. And in fact, as we discussed earlier, the Type 2 curve shows 45% of the total precipitation occurring in the center of the storm. Although the peak discharge will occur near 12 hours for both, the Type 2 curve has a higher intensity through the center of the storm than the NOAA C curve. While it looks minor, this difference has a definite effect on the peak discharge rates associated with the rainfall rates from TP40 versus NOAA Atlas 14. I'll show you this in table form first. I compared NOAA Atlas 14 and TP40 rainfall rates for the 2, 10, and 100-year storms and expected discharges for my location in Baltimore County. That was the Towson station I showed you earlier. For the 2-year and 10-year rainfall events, the values were fairly close. For the 100-year storm event, NOAA Atlas 14 predicted rainfall rates that were 1.5 inches greater than that predicted by TP40. For each storm event, the peak discharge associated with the SCS Type 2 distribution curve was greater than that for the NOAA C curve. Look, this is only one comparison. What this shows us is NOAA Atlas 14 precipitation data may be equal to or greater than the TP40 data. However, because the NOAA distribution curves are less intense than the older Type 2 distribution curve, peak discharges predicted using NOAA Atlas 14 may not be larger than those predicted using TP40. Just updating to NOAA Atlas 14 and changing the precipitation information may not affect current stormwater management quantity management requirements. However, everything that follows is going to be based on NOAA Atlas 14. So we just said the NOAA Atlas 14 rainfall rates for the smaller, more frequent storms did not change significantly. I want to show you that in the next few slides using the same 10-acre residential site to show the difference between the newer NOAA Atlas 14 modeling compared to the older TP40 modeling. For Baltimore County, the NOAA Atlas 14 value for the 2-year 24-hour storm is 3.27 inches. The amount of runoff is about 1.6 inches, and the volume of runoff is 1.33 acre feet. TP40 for this same 2-year 24-hour storm is 3.2 inches, slightly less. The amount of runoff is 1.54 inches, and the runoff volume is 1.2 acre feet. The x-axis is the time in hours since the onset of rainfall, and the y-axis is the peak discharge at any given time x in cubic feet per second. The peak discharge predicted by NOAA Atlas 14 using the NOAA C distribution curve is 13.4 CFS. The peak discharge predicted by TP40 in the Type 2 curve is 16.9 CFS. While the NOAA Atlas 14 precipitation resulted in a slightly larger runoff depth than volume, the predicted peak discharge, 13.4 cubic feet per second, is 3.5 cubic feet per second less than that predicted using TP40 in the Type 2 curve. Let's move on to the 10-year 24-hour design storm. For the same site, the NOAA Atlas 14 10-year 24-hour storm is 5 inches. The amount of runoff is 3.1 inches, and the volume of runoff is 2.57 or roughly 2.6 acre feet. TP40 value for the 10-year 24-hour storm at this location is 5.1 inches, slightly larger. The amount of runoff is 3.2 inches, and the runoff volume is 2.64 acre feet. On this graph, you can show that the peak discharge predicted by NOAA Atlas 14 using the NOAA C distribution curve is 25.9 cubic feet per second. The peak discharge predicted by TP40 and the Type 2 curve is roughly 35 cubic feet per second. Again, because the NOAA Atlas 14 and TP40 rainfall precipitation is very similar in runoff depth and volume, however, the predicted peak discharge using NOAA Atlas 14 is 25.9 cubic feet per second, which is nearly 9 cubic feet per second less than that predicted using TP40 and the Type 2 curve, which is at 35 cubic feet per second. This is understandable again because the Type 2 curve is steeper and has more intense rainfall through the center of the storm than the NOAA C curve. Let's go see how the 100-year storm is affected by this. The NOAA Atlas 14 value for the 100-year storm is 8.65 inches. The amount of runoff is about 6.5 inches, and the volume of runoff is 5.4 acre feet. TP40 for the same storm is 7.1 inches. The amount of runoff is 5 inches, and the runoff volume is 4.2 acre feet. The peak discharge predicted by NOAA Atlas 14 using the NOAA C curve is 53.1 cubic feet per second. The peak discharge predicted by TP40 of the Type 2 curve is 54.7 cubic feet per second. In this case, NOAA Atlas 14 predicted 1.5 inches more rain than TP 40. However, and the runoff depth and volume were also much greater. However, the predicted peak discharge using NOAA Atlas 14, 53.1 cubic feet per second, is still less than that predicted by TP 40 in the type 2 curve, which is 54.7 cubic feet per second. So in summary, NOAA Atlas 14 is the most recent precipitation information available. TP 40 is outdated and no longer supported. How many of us still use a Pentium computer? As we have seen, changing into NOAA Atlas 14 may not affect current stormwater management design much. However, any future updates to precipitation frequency data will build upon the information used to develop NOAA Atlas 14. And NOAA Atlas 14 provides the foundation for many of the climate change models. I'd like to pause here and take allow you to answer some questions again.
Thanks, Stu. In the chat, we had a wow for the photo of your mom.
Thank you.
And post about a call for experts for modernizing probable maximum precipitation estimation. So that's for information. And I see some hands raised. Karen?
Yeah, hi. Thank you very much. So trying to lower my hand here. So can you run this by me one more time? The difference between the NOAA type BCD curve runoff curves versus the Soil and Conservation Services runoff curves, and why NOAA is using the less steep curve?
Okay.
Could just run that by me in shorthand.
Sure. That is the first question I expected. And that's a very good question. Okay, first of all, I have to be honest with you. The origins of the type 2 SCS curve, like a lot of things related to the SCS methods were developed in the 50s, is fuzzy. Okay. And in fact, when you do some looking up, there's like one paper in 1973 that discusses it, but doesn't go into a lot of great detail. However, when they developed Atlas 14, the people that know who are working on this looked at the ratios of specific storm events in across the Ohio River Basin, actually across the country, and they were able to establish specific ratios or bands of ratios of identified storms. I'm not going to go into the details of what they did, but what they found was that there were 4 bands of these ratios that kind of defined different climates, different rainfall distribution patterns. And that's how they developed these NOAA A through D rainfall distribution curves. So there's a lot more confidence in how they were developed and the choices they made in that development than we have with the SCS type 2 curves.
Well, but precipitation is different than runoff. So, sure, there are different bands of precipitation, but wouldn't runoff be a factor of slope and land cover?
This is why I used identical sites. I want to change, if we use identical sites, land use and land cover relationships for the sites will be the same. They will produce the same amount of runoff. What we want to do is look at how that runoff is affected by the new climate patterns that NOAA is using with their precipitation data. It's not just the precipitation data, and I think this is lost, is that it's also how that rain is falling, or not necessarily how that rain is falling, how that rainfall is modeled, which again is a synthetic or hypothetical curve that slowly increases to a central point and then decreases. That's not how it rains. But this is what is used in the design process and in analyzing flooding. And so when they did that, the curves are less steep through the central part of the storm. And so what that does is it produces a slower peak discharge than would have been predicted by TP40. So what basically we're saying is that everything that was designed in the past based on TP40 and the SES distribution curve, is predicting a higher peak discharge than if you use the same values and use the NOAA model. That's what we're pointing to.
So, did they make assumption about slope and land cover in terms of creating this?
That is all factored into other
One size fits
variables
all.
like time of concentration that I'm trying to isolate from this. Certainly those would factor off of the site. But when you just look at a straight up comparison of the two, the change in the distribution curve, even if I had used the same site with slopes and all those same variables, the older method would still predict a different or higher peak discharge than the newer method for identical sites or identical conditions.
Okay.
I was curious, it surprised a lot of eyes in here too. So
Yeah, still puzzling, but I'll keep listening.
it is.
Okay, Eliza?
Did I come off? Hi, Stu.
Hey.
So thanks for a great technical presentation. I tried to follow and hope maybe I got about 20%. So what I'm trying to understand is it sounds like you have a lot of faith that the Atlas 14 model is much better than the older model. That's good. And it shows lower peak discharges, but yet the older pieces of infrastructure are getting overwhelmed by storms now all the time. So is that because our design standards haven't caught up regardless of what the actual peak discharges are? And then I have a related question, I think, which is I watched the webinar for the new tool that we're going to talk about later, I guess, the map. And the person who gave that presentation, and forgive me, I don't remember her name, was saying that the Atlas 14 data sets are really under predictive of climate change driven precipitation impacts. And so that's why they did their effort to update them for the Chesapeake Bay. So when we first got to the webinar today, I was thinking Atlas 14 is useless. It's not predicting climate change, and it shouldn't just be updated for the Chesapeake Bay region. It should be updated nationwide. But now you're saying it's great. It's much better than what we had before, and we really need to rely on it. I'm confused about what is Atlas 14 and how good it is.
Those are two very good questions. Let me hit the last one first. NOAA Atlas 14 is based on rainfall records up to 2000. Okay. So it's backward looking. And so no, it doesn't predict climate change. However, because of the way they developed NOAA Atlas 14, anything they use to build upon it, and oh, by the way, the MRISA tool builds upon it, uses their data, is a foundation. And then you build upon that foundation. So we add newer rainfall data to Atlas 14, to the bank of data that NOAA has. Better predictions can be made. Better judgments can be made because we have much more confidence in the data that was used and how much data there is. So what I'm not saying necessarily is Atlas 14 is great for predicting climate change. We're going to get into that next. What I am saying is that you have to start with a foundation. And NOAA Atlas 14 is that foundation, but you have to understand that when you use NOAA Atlas 14, you just can't choose the rainfall rates that they predict. You have to buy into the whole process, which also includes their rainfall distribution curves. And I think that people look at NOAA Atlas 14 and say, oh, look, the rainfall changed. Well, the distribution curves changed too. And because they're less steep, I'm not going to say they underpredict, they predict less peak discharge than the older method did. Now, your first part of the question was, is our infrastructure undersized? Is it underdesigned? Look, there were a lot of assumptions used for infrastructure design that are still being used, and hydrology is goofy that way. There's several models out there. Road and storm drain inlets are often designed using something called the rational method, which I'm not talking about today. Different people use different design storm durations, like they might use a 24-hour design storm, or they might use a 12-hour design storm, and we'll talk a bit about that as well. Again, this is used for design and does not necessarily reflect what is actually going on. And it was designed for a static point in time, which, we have things changing. And so that's why we find ourselves in this predicament where a lot of our infrastructure may not be capable of handling what we're seeing as far as rainfall patterns. And that's why we're having this discussion. But, the bigger point I'm trying to make here is that just migrating to the rainfall, the newest rainfall rates, NOAA Atlas 14 is not, it's part of the solution, but it is not the solution. It is a necessary step.
Okay, thanks.
Okay, Bill?
Hi, Stu, thanks. You were comparing one site using, or comparing technical paper 40 and Atlas 14 for the 24-hour duration. Did you also look at the shorter duration storms?
Oh, spoiler alert, we'll get there.
Okay.
Yes, I'll talk about it.
Okay, thank you.
And Eric?
Yeah, I mean, my question or comment builds on the last one, which is that, I think, okay, it's great to have the updated precipitation data, and it seems like by all measures, the Atlas 14 probably is an improvement there. But I think this assumption of the normal distribution over a 24-hour a rainfall event is what doesn't seem to be holding very close to the reality of what we're seeing in terms of actual precipitation. And it sounds like Stu is saying that that's part of the future presentation. So I'll hold my comments there, but that seems like that's the variable that really maybe is accounting for the difference between what we're seeing and what the data is showing, at least in terms of precipitation depths that we've got. So I'll wait and see what Stu has to say.
Thank you, Eric. Yeah, I will talk about that in a few minutes.
Bill, new question or old hand raised?
Sorry, I didn't lower my hand.
Okay, thank you. These are all good questions. Good discussion. Up until now, we've been talking about the precipitation frequencies that are based on historical rainfall records. And in fact, as we just said, NOAA Atlas 14 incorporates rainfall data up to 2000. Okay. What about the anticipated impacts of climate change? How will the increases in precipitation affect storm drain and stormwater management design moving forward? Mid-Atlantic Regional Integrated Sciences and Assessments Team, that's a mouthful, has developed a tool for the Chesapeake watershed that projects how climate change will affect precipitation data. This tool is based on NOAA Atlas 14 and provides county-level change factors that may be applied to the NOAA Atlas 14 rainfall rates to adjust for climate change-related impacts. The tool also provides updated IDF curves for the individual stations used to develop the tool. So there may not be IDF curves for every county in Maryland, because they did not use stations located in every county. The tool, which is available online, provides projections for multiple scenarios and time periods. It provides a low representative concentration pathway, or RCP 4.5, and a high representative concentration pathway, or RCP of 8.5. Both of these scenarios are extended through two time periods, 2020 through 2070 time period, and a 2050 to 2100 time period. And again, it is available online. Somebody posted the link in the chat box for me. Thank you. And it is here on this slide. This is a screen capture of the Marissa tool showing the various stations used in the development of local projections within Maryland. It's hard to see Maryland in this dark green pattern here. The dark green, the various shades of green showing the median county change factors. As you can see, for some counties, Allegheny, Frederick, Carroll, Baltimore, Howard, there may not be a station that they used. For these counties, they predict change factors. Where they do show stations, they actually have produced IDF curves. This is a comparison of NOAA Atlas 14 with the Marissa projections for each county. Because there are not IDF curves for each county, I have used the average of the median change factors for the 2, 10, 100-year, 24-hour design storms. They actually provide change factors for each level storm. To make this a little easier to relate to, I've averaged those change factors and used them in this table. For all cases, the Marissa projections are larger than the currently used rainfall rates. As you can see, the average Marissa change factor ranges from 14 to a 20% increase. So if we apply these Marissa projections, how would this impact our rainfall modeling? This table summarizes how each of the different Marissa climate change scenarios affects the peak discharge that may be expected from a 10-year, 24-hour design storm falling on an identical site. And again, I do this because I don't want site conditions to affect the comparison. So if I use the same site and isolate all the variables, we see the changes. This is important because our current stormwater quantity management systems and storm drain conveyance are designed based on the current rainfall patterns, and in most cases using a 10-year, 24-hour design storm. And these same systems may not be able to handle the increased flows. Regardless of the scenario selected, there will be increases in rainfall and peak discharges. The magnitude of those changes is dependent on the scenario selected. Currently, we are still discussing which scenarios should be used. Some of the factors in that decision are the design lifespan of infrastructure. Typically, we design capital projects to have a lifespan of 50 years. And representative concentration pathway 4.5 is a mid-range scenario that may better represent conditions where there is a stabilization of global temperatures. However, we haven't decided on anything yet. We are still considering the options, and we are also discussing the implications of these options with the Regulations Technical Advisory Group. This is the hydrograph comparing the NOAA Atlas 14 to the Marissa climate change projections for the 10-year, 24-hour design storm. For these comparisons, I've used the same 10-acre residential site that was used in earlier examples. I have used the high RCP 8.5 scenario, the 2050 to 2100 time period, which represents the highest estimate of climate change, and the low RCP 4.5 scenario, 2020 to 2070 time period, which is the lowest estimate. Again, the x-axis shows time in hours since the onset of rainfall, and the y-axis shows discharge in cubic feet per second. The peak discharge as predicted by NOAA Atlas 14 for this site for the 10-year, 24-hour design storm is 25.9 CFS. The peak discharge as predicted by the Marissa tool range from 29.3 cubic feet per second to 33.4 cubic feet per second. Based on this information, we can see that the runoff depth, volume, and the peak flow or discharge from the 10-year, 24-hour storm is predicted to increase moving forward. So again, Marissa tool is based on the NOAA Atlas 14 data set. How we are going to use this tool, we're still discussing this, okay? Marissa tool does provide intensity, duration, frequency curves for the reporting stations. It provides change factors for area where reporting stations do not exist. We know that rainfall, runoff volumes, and peak flows will increase as a result of climate change. However, we are also aware there may be better projections in the near future. We understand that NOAA Atlas 15, NOAA is working on new guidance, and that will also include climate change projections. NOAA Atlas 15, we understand, may be available by 2025. Okay, I'm going to pause again before I move forward and take questions, and I know that there's a couple of questions here. So go ahead, Kathy, go ahead.
Can you see the questions in the chat, Stu? I'm going to read them. We
Okay,
have
please
one.
read them.
What is an Atlas 14 change factor? And maybe it would be helpful if you scroll back to where you use that term.
Okay. Give me a second. Tell me where to get there. Here. Okay. All right, the Atlas 14 change factor, the Marissa tool, to be fair, it's the Marissa tool change factor, is the percent that they predict a specific storm, in this case, whether it's a 2-year 24-hour storm or a 10-year 24-hour storm or a 5-year 12-hour design storm, will change as related to climate change. So they don't necessarily say in the future, this is the rainfall that will occur. Rather, they say, in the future, it is likely that this frequency storm will have increased by 20% or 1.2, it's increased by 20%. So we would then multiply the NOAA Atlas 14 rainfall projection for that storm. In this case, if I chose 3 inches and multiply that by 20%, that would be the new storm that we could figure for climate change purposes. This is done because, again, they have a confidence band of these statistical analyses that they've done, and they don't want to at this point say, oh, it's going to be this, but we know it's probably going to be within this range. Does that answer your question? Okay, let's go to the next one.
Okay. Although capital projects have projected lives, we should also consider how much time passes after the effective life of a structure before we actually update or repair or fix it.
I'm not going to disagree. Clearly, we plan for a lifespan for a lot of our infrastructure as being 50 years, but this is a problem we're still facing across the country, as we have a lot of older infrastructure that hasn't been replaced that is outside of that lifespan. However, again, that's one of these risk assessment or design judgments that's made in the process of developing infrastructure. And that we will discuss as we determine which scenario to use for climate change, whether we use the 20 to 2050 or we use the one that's further out. That's still in discussion.
Okay, the next question. You just mentioned Atlas 15 will be updated by 2025. What will that mean for Marissa? Will the new Atlas be less stationary and applicable to climate change?
Those are all good questions, and I hopefully you'll know the answers when NOAA Atlas 15 is released. I do know that they are considering climate change projections. However, the last I heard from NOAA was that they too were reluctant to point to a specific number and would rather say it's going to be a change factor of X% moving forward. So we will not know that until we see more, until the curtain is revealed on NOAA Atlas 15. We just know that they're working on it.
Okay, and we've got a raised hand. Eileen, go ahead. Oh, you're muted.
Thanks. Hi, this is Eileen Craig with the Nature Conservancy. Thank you, Stu, for walking us through that. Could you go back to the slide that shows the comparisons for a second of the Marissa?
This one?
Yes, I guess I'm curious. It looks like even with the climate change effects, the peak discharge for the Marissa worst case scenario going out to 2070, 8.5 is still lower than the TP40. So just curious how that's factoring into your decision to use Marissa versus other methods.
Okay. Before I would use that to influence any of my decisions, I would have to do a lot more modeling of different conditions across the state to find how what trend this was showing us. Again, we have not had the ability to do that level of detailed modeling yet, but I wanted to compare TP40. And I'm glad you picked up on that, because again, the older distribution curves, because they are steeper through that central section, do predict more runoff. However, again, I would have to go across and do this for the same, each county and the new rates, and determine if there was a trend before I would even consider factoring that into projections moving forward. I think at this point, I personally, on a personal note, would rather just push TP40 aside, say, okay, that's the outdated information. Let's look at making decisions based on the new information moving forward, and then deal with how that is going to be affecting older infrastructure. Because, the more I read about how they developed those methods, the more I like the newer stuff.
Okay, Thanks, Stu.
And I see Jennifer, you have a hand up? Thank you.
Good afternoon, everybody. Yes, Stu, I was just thinking that it might be a good time, and I know you're going to get into it next, to say that we are looking still here at a 24-hour duration storm event. And Atlas 14 does have other duration storm events in the data set, and we've only been comparing the 10-year 24-hour duration storm in this particular slide. And throughout this presentation, we've been talking about the 24-hour duration storm. And I think it was Eliza that mentioned that, or maybe it was somebody earlier, that we are still seeing, even if we went to something like NOAA Atlas 14, if we're looking at peak discharge rates that are going to be predicted as lower, how is this addressing the fact that many of our storm drain systems are under capacity and are flooding? And I think that, I guess I just wanted to point that you will be getting to that next, but that is a very important thing to think about as Stu goes forward in the next part of this presentation.
Yeah, I think as I move forward, it is good to keep reminding yourself that the vast majority of rainfall data that has been reported to develop both technical paper 40 and NOAA Atlas 14 has been 24-hour data. You hear me say it a couple times. It rained 3 inches yesterday. That tells us very little about the nature of that rainfall, other than it rained. Historically speaking, for these reasons, the engineering community has used typically either a 24-hour design event or a 12-hour design event for most of their design purposes. So, there's this ingrained behavior that we use these events. I'm not going to comment right now on whether or not that is right or wrong. You just have to understand that it is. That's what the traditional design has been based on for, since the 40s and 50s. So with that, and that's a good segue, and I see Neil's got his hand up, so I'll go ahead, Neil. You're muted. Neil, did you have a question? Stu Schwartz has a question.
Well, yes, Stu, just a quick comment. The Marissa estimates provide a single factor. That's the ratio of their mean estimated rainfall change from TP 14 to whichever climate change period they're looking at. That's how they chose to do it, and there are a number of reasons for that are documented in their report. But I think it's important to keep in mind that there's no a priori reason to believe that the percentage change in rainfall depth across storms of all recurrence intervals will have to be a single number as we project out 50 or 75 years. That just happens to be the way Marissa has done it. There have been quite a number of other studies asking these same questions that have come up with very reasonable, grounded, physically based explanations of why the percent increase in depth for whatever climate scenario you're looking at will be different for the smaller, more frequent storms than the larger storms. So that single factor is just an artifact, if you will, of the method used by Marissa, but we shouldn't get too locked in on that idea of a single number.
Thank you. That's a very good comment. Are there any other questions before I move forward?
Let's check with Neil one more time.
Yeah, Neil.
Okay, and then there is a question in the chat.
I'm sorry, I had to step away for a second.
Oh, okay.
I think I posted it to you, Stu.
Okay.
So we're using something that's those models like that we're using like for TR55 or TR20. I mean, those things are only accurate within what, 20-25%. I think that's part of the documentation. So we're coming up with something that's very much more rigorous. So how do we account for all that variability?
That's a good question, and in the interest of trying not to lose my audience within the first
Yeah, you can
hour
do
of
that
the
later.
presentation today, you notice I said we're not going to talk about hydrographs and how they're developed. Let me just say for everyone involved, there are a number of hydrologic models out there that are used, and they all have a different purpose, and they all were developed to tackle different situations. I mentioned the rational method is one that's often used with highway and roadway design. There's one called WindSlam that is the foundation of the simple method that was very good for developing water quality volume projections. There are the TR55 and TR20 that were developed originally by the Soil Conservation Service, now the NRCS, for predicting flows, river systems, for flood modeling that have often been used for developing stormwater management designs because they're reproducible. Each of these models has factors that, for lack of a better term, might be considered fudge factors, and have different effects on how the results will be. I just want to point out that these are part of the assumptions of the risk-based assessments that we have to look into as we discuss moving forward, changing the stormwater management program, is the appropriateness of specific models. This is no different than what we tackled back in 2000 when we switched to the simple method for determining volumes from smaller storms. So again, these are issues that are under discussion with the regulated industry and the regulations technical advisory group. We're not hanging our hat on any one specific model, but I think when I'm trying to convey what some of these changes mean, you kind of have to stick with one model and say throughout the presentation, we're just going to look at this one so that you can see the trends or at least some of the issues we're seeing, recognizing that, this may not be the only model that we're using. Does that help you, Neil?
Yeah, that clears up a lot of stuff. I understand that.
Yeah.
Thank you.
Okay, Stu, one more question from the chat. So if we want to design to say the 3-hour storm with current NOAA data, that would just be 3 hours worth of the 24-hour data. How would we develop data for shorter duration storms?
That's Karen, that's a good question. Again, I think my original presentation had a whole section on how they take a 24-hour design storm and trim it or cut it to predict what would happen in a shorter duration storm. But like the development of hydrographs, I figured if I started going down that rabbit hole, I would lose 98% of you, and those who really get a kick talking hydrology would be the only ones left. Suffice it to say that this is an issue that I'm going to talk about in a little more detail very shortly. And that is at the crux of one of the issues that we are wrestling with moving forward with the stormwater management program, is that we do need a better way of determining what shorter duration storms look like. So that's a nice segue into the next section. Are there any other questions before I move forward?
I see something from Stu, but 3-year precipitation is not 3 hours of the 24-hour precipitation. I guess
Yes.
that's just a response. Okay.
3 years of frequency. The 3-year storm may, depending if it's a 24-hour storm or a 12-hour storm, could be different precipitation amounts. 3 hours of the 24-hour storm is a different issue. So if I may, I'm going to move forward. Let me go back to where we were. Okay, we were here. This is an older picture that I took many years ago walking out of the Montgomery Park office building. It's very infrequently that you capture lightning in a bottle, but I just got lucky that day. I liked this slide because it is not raining where I am standing, although it will be shortly. And then I think it rained for all of like 5 or 10 minutes. And then when I drove out of the parking lot, it had stopped raining. Actual storms can be of any duration. It can rain a lot in a short time. It can rain a little over a long period of time. Design storms of specific lengths are used for engineering purposes so that we can reproduce results. we make specific assumptions and decisions when we use these design storms. For example, as I mentioned earlier, a 10-year storm has a 10% chance of happening in a given year. So we take the risk that 10% of the storms that may happen in that year might exceed our design requirements, and that's acceptable or not acceptable. That's a decision we have to make. The 24-hour storm is the most commonly used. There are other storm frequencies. If I pulled up a copy of NOAA Atlas 14, and I can go back afterwards and show you this, there are 5-minute storms, there are 30-minute storms, there are 24-hour storms, and there are 3-day storms in their prediction and their tables. However, again, because most of the data that comes in is 24 hours, and this is especially true historically speaking, the 24-hour storm is the most commonly used for design purposes. Now, we know that this is an issue, but how does it affect our regulatory requirements? Staff compiled this information from public sources. And from this, you can see that many of the intense storms in the past several years occurred over 1 or 2 hours. They are not 24-hour storms. They're 2-hour storms or 3-hour storms. So I just want to take a few moments talking about how storm duration affects the peak discharge or flow from one of these storms. Again, storm drain and stormwater management infrastructure is commonly designed based on a 10-year, 24-hour design storm. For our site in Baltimore County, the 10-year, 24-hour design storm just happens to be 5.2 inches in 24 hours. If you will notice here, I have, for Clear Spring down here, 5 inches of rainfall in 2 hours. So if we use our sample 10-acre residential site, we can show the difference between these two storms and what the results would be using the standard hydrologic and hydraulic models that we design stormwater management practices with. Both storms will produce 3.25 inches of runoff and 2.7 acre feet of runoff volume. However, the peak discharge is markedly different. This hydrograph shows you just how much. Again, the x-axis shows time in hours since the onset of rainfall, and the y-axis shows the discharge in cubic feet per second. The predicted peak discharge for the 2-hour storm is 51 cubic feet per second. The predicted peak discharge for the 24-hour storm is 27.3 cubic feet per second. Please note, the volume of runoff, this 2.71 acre feet of runoff, it's the same for both storms. It's the area below these curves. So all this area down under here is the same as all this area under here. In the shorter duration storm, 2.7 acre feet of runoff passes in about 3 hours. All of the runoff that storm generated passes in 3 hours. For the 24-hour storm, we're not even seeing runoff until about hour 8. And then that same volume of runoff passes in over 10 hours. Here I am in hour 18, and I'm still getting some runoff going through the system. Clearly, practices designed using a 24-hour storm may be undersized for shorter duration storms. If I've got an inlet system that's designed to capture 27.3 cubic feet per second for a 24-hour storm, and I am getting 50 cubic feet per second for a 2-hour storm, that inlet is not going to be able to pass that runoff, and it's going to back up. The difference here is 11 hours between the peaks. This is exactly what a lot of you have been questioning about. So clearly duration does matter, and it's one of the issues we're talking about. Again, we are talking about storm duration with the Regulations Technical Advisory Group. However, I can tell you, there's limited information available concerning shorter duration storm events. This map shows the weather stations that were used to develop NOAA Atlas 14. As discussed earlier, 78 of these stations reported daily information only. So out of 93 stations, 78 of them said, hey, it rained 3 hours yesterday. This map shows the 28 stations that are currently reporting hourly rainfall data to NOAA and the National Centers for Environmental Information. Of these, 17 are located at airports and 1 is located at Camp David. A famous comic once remarked that nobody lives at the airport. Of the 10 remaining stations reporting hourly data, 2 are located in Annapolis and 2 are located in Baltimore. So that means there are 6 stations in residential or built areas that are reporting hourly data to the National Centers for Environmental Information. Also shown on this map are the 4 locations represented by the teardrops: Clear Spring, Ellicott City, College Park, and Forestville, where short duration heavy rainfall events were reported. It is ironic that 2 of these storms, College Park and Forestville, actually occurred near an airport. So we actually have probably hourly data for those events. The department understands that others, including the Maryland Department of Emergency Management and local academia, are working with hourly and small-scale data, mesoscale data. Atlas 14 is based on rainfall information up to 2000, and the majority reflects daily total rainfall records, not hourly data. Of the 93 stations in Maryland, 16% reported hourly data. So you can see that one of the reasons we don't necessarily work with shorter duration storms, or have not historically worked with shorter duration storms, is the information is just not there. But the work that we are seeing moving forward will help us paint a better picture of local rainfall patterns. And we hope that that can be used in watershed management studies that we can then use to develop better stormwater management requirements locally. So again, the information that was coming out based on shorter duration storms and mesoscale data, which is, how different regions in the state are working, will be used to refine the state stormwater management program. How it will be used to refine the state stormwater management program is something we are still discussing internally and with the Regulations Technical Advisory Group. So I could say, if my inlet has a capacity for 27.3 cubic feet per second, what duration storm events could it convey besides the 10-year 24-hour storm? And again, these are things we could model. So with that, I'm going to pause again and take your questions.
So Stu, we had 3 questions in the chat, and I'm going to invite Karen to come off of mute, unless that was just a comment that you wanted to make and you don't want to expand on it.
Right. I think there was some chat between me and someone else in the chat, but yeah, I think that confirms that the 24-hour interval in the data in NOAA Atlas 14, if a person were to go and look at the chart and look for the 3-hour, it's just a smoothing. It's a 3 hours worth of the 24-hour amount. And I think Stu just confirmed that because we don't really have very much hourly data collected to actually have 3 hours worth of rainfall measured.
Yes. Let me go back to that table. That's why I'm
Thank you.
Scroll back. Okay. This chart here, this is what NOAA Atlas 14 produces if you want to see the precipitation-based frequency estimates for 90% confidence for durations ranging from 5 minutes to 60 days for a 1-year through a 1,000-year storm event. Again, these are based on statistical analyses, of the existing rainfall data. They may not have 5-minute rainfall records. As you can see, only 16% of the stations that they used in Maryland to report this information reported hourly data. And as I said, only 28 stations currently report hourly data to the National Center for Environmental Information. So again, the way they develop these is through statistical analysis of the data they have. So, again, these are engineering or hydrologic guesses of what that frequency storm might be. So for, I'm going to go with a 2-hour storm. If I were to say a 2-hour, 10-year storm for this location would be 2.58 inches of rainfall. That would be right here. Again, that's still not the 5 inches that we saw in 2 hours. That 5 inches in 2 hours might be right over here. That's a 500-year event. So you can see that the frequency estimates we have, these are just recurrence intervals. The odds are that that storm has of occurring in a given year. Doesn't mean that it's not going to happen. It's just the odds are pretty slim.
Sure. Would it be possible to just take those 16 stations and just to see like if they're seeing a shift in how these shorter duration storms from, I don't know how long they've been collecting that data, 20 years ago versus now, or 30 years ago versus now, as an exercise to see if we're seeing those kinds of shifts in actuality because there's more of these big cloud bursts of rain coming down, at least anecdotally.
There are efforts underway, both, I believe, at University of Maryland, and I know at the University of Maryland, Baltimore County, UMBC, and at the Maryland Department of Emergency Management, among others, that are doing just exactly that. Okay. However, these efforts are underway. We don't have the results from a lot of this work yet. And so again, this is why, when we talk about modifying stormwater management, quantity management requirements, we are a little reticent because we think that, as you guys are seeing, we think this is important as well. But we don't quite know how it's going to play out yet. So we're kind of very closely watching this and discussing the implications of this moving forward.
Okay, and Jen's question is, if duration does matter, is anyone collecting data on if/how storm duration has changed over time?
Again, that is something that is being done outside of our little shop. Forgive me, I'm going to, I don't think that my staff is equipped to do that, but we are very closely watching those that are doing it, including NOAA through the development of NOAA Atlas 15 and local academia and Maryland Department of Emergency Management. So when this information becomes available for our use, we will certainly pore over it very intensely.
Okay, and one more from Eric. Is there a way to work back from USGS gauging station data to try to estimate precipitation duration historically?
Eric, I'd have to look up that one. I can't answer that one for you right now, but I can try to find an answer for you. I'm certain there's a way, but I don't have an answer for you right now.
And Josh has a hand up.
Yes, Josh. Are you? We can't hear you. Are you muted?
Can you hear me now? I got to unmute the headphone set and the 10 unmutes.
Too much technology.
Yeah, exactly. So you mentioned the MDEM work, and I'm just wondering, kind of if you could just briefly tell us kind of what they're doing and how that then could be applied if they're thinking about like big flooding events, or how that could be applied for us when we think about stormwater management, just so kind of get the better sense for the landscape, right, of all the potential tools and data sources.
Yeah. I am aware that MDEM is doing that work. I do not know the details of that work. If there's someone from my staff or from our program that has that answer, and they want to speak up, please let them do so. Otherwise, I will have to get you that answer later, okay? But I do know they're working on it. I see nobody from my staff wants to jump in and answer that question for me. I will get an answer for you. Any other questions?
I don't see any.
Let me get back to where we were. Sorry for making you all dizzy. Okay, so what's next? Put all this back in perspective. The department is moving forward with adopting NOAA Atlas 14 as the official source of precipitation frequency data. This will most likely be done through an incorporation by reference into the stormwater management regulations. The reasons we're doing this, first and most obviously, TP40 is no longer supported. Let's get out of here. NOAA Atlas 14 is the foundation for all the climate change models. These models are critical for determining changes to the state stormwater planning management program. And hey, some jurisdictions are already using Atlas 14 for stormwater management or storm drain design. We are discussing if climate change projections should be used, which ones should we be using? Okay. We don't have an answer for you yet on that front. We are still discussing which ones we should be using. And we are very much discussing new information, including mesoscale data and shorter duration storm events are needed to better characterize rainfall patterns in Maryland. The Regulatory Technical Advisory Group has broached the topic of using shorter duration storms for our regulatory requirements. We are discussing this. Okay. It is a long and deep discussion, and I don't have an answer for you at this point in time. But we are discussing the implications of shifting to shorter duration storms. We are still in the early part of a race. This is me at mile 3 on Annapolis 10 miler a couple of years ago. And, you know, you think, great, I'm at mile 3, but then you realize I still have to cross that stupid Severn River Bridge twice. And the whole back half of the 10 miler is up and down hills. There's a lot of work to be done. So as good as I feel at this point, I know I've got a long way to go before I finish this. So again, we are still discussing this. There's a lot to discuss. We need some more information. But again, I think the first thing we can and should be doing is adopting the latest rainfall data so that we can move forward and not be still tied back in the past. With that, I would like to I want to thank you all for listening to me today. I would like to hand the presentation back over to Kathy.
Not so fast, Stu. Yeah, we got a couple of things in the chat.
Okay.
You got a answer to your item number 3 on the previous slide, I believe. Yes, please. If you want to go back to what was it on the what's next slide?
Okay. Answer to item 3. Yes, please. What's next slide? Okay.
And then, yeah, there.
Yes, it's looking more and more likely that we will be looking at shorter duration storms. It has a number of implications. How we address that, whether we do it in regulation, whether we do it in the confines of the design manual, that's also under discussion. Just that change alone is it's a major change. It affects a lot of different pieces of the puzzles. We have to be careful how we do it. That's all I could say about it at this point in time. There's another one here. Parts of MDE have been using Atlas 14 that was released in 2006. For example, if you go in for a wetlands and waterways permit or flood management, yes. Again, we did not in the stormwater management side adopt NOAA Atlas 14 as the official rainfall precipitation data for use for stormwater management, because even then we were aware that the changes didn't affect much for the existing stormwater management quantity program at that time, and that also recognize that the current regulations, local jurisdictions are responsible for implementing quantity management. They should be doing so if they have local flooding issues. The state backed off and did the the unified sizing criteria. And so for many reasons, we did not address the change in 2006. We're going to fix that. I got 4 new messages here. Laugh out loud. Okay, I like that. I thought it was already determined that climate change will be considered, but how is it still being discussed? I didn't realize considering it all was on the table. Don't get me wrong. We are looking forward at climate change and discussing how to implement and change the stormwater management program to address the effects of climate change. There's topics here like which scenario do we choose? That makes a difference. You know, do we use a middle of the road scenario? Do we use a worst case scenario? Which change factor do we adopt? There's change factors for each different storm. But I think what we're seeing here in the discussion is it's not necessarily a 24-hour design storm that maybe we should be targeting. Maybe we should be targeting a shorter duration storm. And I think equally important, which we haven't really discussed today, is this idea that maybe we should be tailoring stormwater management, quantity management requirements to address climate change on local issues and local infrastructure, which is going to require watershed management studies, which, you know, was not even under discussion today. So I think that, yes, we're going to be addressing climate change, but again, it's not like we can just, you know, make those changes in a day. It's going to require a little bit more discussion on how that happens. Do I get to say next now?
Oh, sure, yeah, and there was one other question, and maybe we'll get to that when we go through the next steps. So
I have an answer to the MDEM question. Kevin Wagner from our flood management division has posted that MDEM has secured funding for Mesonet 98 stations starting next year. This will help a lot towards characterizing shorter rainfall events throughout the state of Maryland. That's a lot better than 28. Thank you, Kevin.
okay, you can go to the next slide, Stu. Thanks. So starting to wrap up, everyone here today, members of the stakeholder group, as well as members of the public, will get a link to the recording and a follow-up email from MDE through the Hughes Center. We'll meet again with the stakeholder group virtually on November 15th to continue this discussion. We'll get into the connection between the technical information and regulations. Stakeholder group members will have an opportunity to submit comments after that meeting. So Karen, that might be getting at your question there. When do you get to talk back to us? So in the spring, we'll do a formal promulgation, including public review and comment. And we expect to follow a similar process with future stormwater regulation changes. So this is not the end. Next slide. For our public participants, you'll be invited to the November meeting. And in the spring, you'll have an opportunity to review and comment on the draft regulations. And you can always check the A-StoRM Hub for any new information. Next slide. Any final easy questions from anybody at this point?
Yeah, I have a question.
Okay.
I couldn't quickly raise my hand, so I just spoke up. So just to be clear, so we only get, we don't get to discuss recommendations with you during the next call. We have to wait and submit public comment. Is it, are you planning time for us as a stakeholder group to have a conversation?
I think we'd be interested in opinions on that. It would probably involve having another meeting. So if others want to weigh in by emailing Ray on that question.
Because I feel personally like I have thoughts on how I might answer the question, but it's sometimes helpful to have a back and forth to kind of weigh ideas and also to clarify information that I may misunderstand.
So I'm going to jump in, Kathy. Yes, the next meeting, the November meeting, we'll have more time to have a back and forth conversation about what Stu has presented today. There's also additional information that we want to talk about, technical information that we want to talk about in November as well. We want to talk about what quantity management requirements we currently have in place and what some of this information today that we discussed regarding the different design storms means when it comes to quantity management requirements. So, but again, we want to allow time for this stakeholder group to have a conversation amongst yourselves too. So that's sort of the intention for the November meeting.
And I'd like to jump in too, if I may. Karen, you can email me any questions, and anybody on the stakeholder group really can. We really slowed this down, and I hope you all appreciate what we're trying to do here, to bring the science forward. I think the questions, like a lot of you were saying, I'm barely getting this, but I think you were getting it. We're really trying to determine whether this 24-hour storm duration should be the foundation of our program moving forward. And we thought the only way of doing that was to have slow things down and take a subject that's very technical and bring it home to more of us. So I think that was a victory today. But if you have additional questions, either technical or if you're beginning to think how this could parlay into regulatory changes for our stormwater program and the design of our BMPs and the design of our conveyance systems, definitely you can send them in to me. We can begin that dialogue. But within 1 month, we're going to be presenting some more of that. And then there will be an opportunity for you to comment. This is your group. We're here to serve you. If the group thinks that after the November meeting that an additional meeting is warranted, or some process moving forward for that back and forth exchange, we're open to that. Share those ideas with me now and after the November meeting. Thank you.
Thanks, Ray and Jennifer. And thank you to everyone who participated today. And thank you to the Hughes Center for hosting. And I guess we'll conclude this meeting and we'll stop the recording now. Thanks, everyone.